All right, let's get started. So today our main topic is about functions and relations. But before I start, I have a bunch of announcements. First of all, the TA has finished its grading most part of quiz number 2, and you will see the grades either tonight or tomorrow morning. And then homework 3 is due this Friday, and then homework 4 will be released also. A reminder that quiz number 3 is going to be on October 20, which is 2 weeks from today. And it's going to be on the sets and Boolean algebra, which is chapter 3 of the textbook, and lectures 8, 9, and 10. Again, as before, it's going to be between 7:30 a.m. and 4 p.m. And you have 1 hour window to solve the quiz and additional 30 minutes to upload. So there's an important announcement which you can read the detail on Canvas. Specifically for quiz number 2, we have detected several instances of cheating, but we're offering this one-time scenario where if you let Professor Zivang know, here his email address here. If you let him know by midnight tonight and admit the cheating, then you will just get 0 points for quiz number 2, and we'll move on. But if you do not, then we will start with the departmental procedure, which leads to failing this course, and it will go on your record. So anyway, so if you want more detail, please read the announcement over Canvas. All right, before I start with a practice problem, any questions? Okay, all right, if there's no question, let's look at a combination of proof techniques together with set properties. Okay, and to prove that the following sets are subsets of each other. So you have 1 minute to think about how you might want to prove this problem. I'll start the timer. You can start now. Okay, so just a quick hint for this problem. If I were thinking about proof sketch, there's a few properties I'm going to use. I'm going to prove using set membership. I'm going to use a definition of union of set and a definition of subsets. Those are some ingredient for this problem. And I'm going to simplify my notation by defining the first set to be set A, the second set to be set B in the problem definition, and set C is the one on the right-hand side. Those are all real numbers. And then the problem is we want to show A union B is a subset of C. Okay. All right. Do I have a volunteer how we want to prove this? What you just wrote here, if I want to show A is a subset of B, I'm going to choose an element in A and show it's also an element in B, right? So essentially this is for all element in A. Okay, do I have a volunteer? What is sort of the main idea to try to do this proof? All right. I guess people are still recovering from the weekend. I'm just gonna go ahead with this. So in order to show a subset, we start with the element on the left-hand side and show its element on the right-hand side. That's what we want to do. So what we have, we can say we have element A that is in the union of those two sets. And our goal is to show it's also an element in C. That's it. But remember, the first ingredient is to understand the union. If A is part of A union B, that means A is in A or A is in B, right? So that means we have two cases, A is in A or A is in B. Those are the two cases. So I want to show if A is in capital A, it's part of C. That's the first part, okay? Okay, so now what do we do? If A is in capital A, this means A is smaller than -7. That's by definition of the set A. If I add 3 on both sides, that means A plus 3 is smaller than 0. If I minus, let's see. If I minus 3 then both sides, it also means A minus 3 is smaller than -3, is smaller than 0. So now what do we have? So we have both A plus 3 and A minus 3 being negative. Now, if I multiply two negative real numbers together, I get something positive. Which means A squared minus 9 is bigger than 0, which means A is in C. So what kind of trick did I do? If I'm going to use a different color to highlight the trick I used a few properties. Not only just set membership, the definition of union, definition of subset, I also use the fact that A plus B times A minus B is equal to A squared minus B squared. That's the first thing I used. The second thing I used is that if A is smaller than 0, B is smaller than 0, two negative numbers, when they multiply together, I get a positive number. That's another property I used. Okay, that's what helped me with the first case. So now let's do the second case. A is part of B. By definition of the set B, that means A minus 3. That means A is bigger than 3. Okay. Oh, I didn't mean that. So do I have a volunteer? What do I do? Using the same trick as I did. If A is bigger than 3, what is a sign for A plus 3 and A minus 3? Anyone? Remember in the previously, when A is smaller than -3, I can do some algebra multiplication by adding 3 to both sides, or subtract 3 from both sides and not changing the sign of the inequality. Okay.
So Dylan in the chat said A minus 3 is greater than 0.
Perfect. Right, that is one multiplication. I can also do A plus 3, which is bigger than 3 plus 3, right, which is bigger than 0. So now I have both A minus 3 is bigger than 0, A plus 3 is bigger than 0. So we have both A plus 1 and A plus 3 minus A plus and A minus 3 being positive. So I have two positive real number. Therefore, A plus 3 times A minus 3 is equal to A squared minus 9 is bigger than 0. I have two positive real number, multiply them together, it's also positive. So this means A is squared is bigger than 9. This means A is part of C. So now I have to prove both cases. Then I prove the original statement. Okay? Because I need to prove when A is in A or A is in B, A is also in C. Of course, I have typed in blue. This is what you need to pay attention when you actually write the proof in detail. The few important part, I'm going to use the formula A squared minus 9 is equal to on the high level, this is a squared minus 9 is equal to a plus 3 minus times a minus 3. That is one of the algebraic trick we used. The second trick we used is you have two negative number, multiplying two negative number gives a positive number, and multiply two positive number gives another positive number. Those are the two important part of this proof. Okay, any questions? If there's no questions, now let's look at a question surrounding functions. You have 1 minute to solve this problem. The idea is my set is set A, B, and C, and a function defined mapping from P of X to P of X. What is P of X? P of X is a power set of X. That's P of X, okay? So the domain of this function is a power set of X. The codomain of this function is also the power set of X, or sometimes people call it range, is also the power set. And now what I would like you to do is to look at the set diagram, arrow diagram of this function, where the function is defined, where A is a variable. So for any A, capital A, which is an element in the domain, which is an element in the power set, we map it to a set difference. So what does this mean? If A is a element, is a one set, is a set with one element, which is an element in the power set of X. Okay. I want to show that if my relations or function C map to A, function C map to the element is equal to X set difference of this A, which is equal to, anyone? If my set X has 3 elements, I take the set difference between X and then the set with 1 element. What is my result? It's BC, right? Because this is what's in X but not in A. So in order to draw this, what I'm going to do is I'm going to do the set, which are both the power set of X, and my function is C that map element from one to another. So can someone tell me what are the elements in the power set of X? Do I have a volunteer?
So in the power set of X, you have the empty set, and then you have A by itself, B by
Remember
itself.
the parentheses.
Oh yeah, the curly braces B, and then curly braces C, and then you have AB, AC, and then BC, and ABC.
Yeah, perfect. So now I'm going to copy the same thing on the right-hand side because that is a codomain of my function, which is also the power set. Okay, so now I'm going to draw an arrow of mapping from one to another, and I'm going to use different color to differentiate. If I start with my empty set, where is it mapping to? By the definition of my function. Do I have a volunteer? What is C of empty set?
Peter in the chat said ABC.
Yeah, it should be the set itself, right? It's everything in the set, but not in the empty set. So if I'm using my diagram, I draw arrow. Empty set map to ABC. What about the element A? Where does it map to? Again, I'm taking set difference, right? I kind of already give a hint over here.
It's BC in the chat. Many
Perfect.
answers.
What about B?
AC.
Perfect. What about ABC?
The empty set.
Perfect. Okay, so as you can see, I'm just really matching a set its complement throughout this process. And what I have drawn is the two-set arrow diagram. Then let me ask an additional question. Is this function C invertible? Is this an invertible function?
Yes, in the chat.
Okay, great. It's invertible because it's 1-on-1 and onto. Okay? Any questions so far? Okay, so my next question is to ask you to prove a function is invertible. To prove something is invertible, you need to prove that it's one-to-one and onto. You have a minute to think about it, but while you think about how to solve this, I'm going to quickly review what is one-on-one and onto. This is a very important concept, and you're going to use it later in some other classes as well. So a function is one-to-one, or sometimes it's called injective function, if it satisfies the following. Let's say my function is going from x to y, where x, y are domain and codomain. F is one-to-one if for all element, pair of element in the domain, if they map to the same element in the codomain, it implies those are the same element. If I look at this statement, I can also talk about its contrapositive. So equivalently, it means for all AB in the domain, if A is not equal to B, it implies FA is not equal to FB. What does this mean? This means that distinct element in the domain map to distinct element in the codomain. That is one-to-one function mean. So let's draw some pictures. So I have the following function. So 1, 2, 3, A, B, C, and D. Is this function one-to-one? You can type, you can raise your hand. Is this one-to-one? Remember, distinct element in the domain map to distinct element in the codomain.
Parker said yes.
Exactly. How do you check? It says for any element which is not equal in the domain, they map to distinct element in the codomain. So yes, this is a one-to-one function. What about the second one? What I just draw? Is this a one-to-one function?
Elizabeth said yes. Lots of people said yes.
Yes, in fact, this is a one-to-one and an onto function. But we're going to define onto function or review it very soon. What about the third one, which I'm drawing here right now? Is this a one-to-one function?
No.
Why?
There are two elements mapped to C.
Exactly, because 3 is not equal to 4, but they both map to C. That does not satisfy the definition. So this is not one-to-one. Okay? But what about I add an extra element D here? Does it change the function being not one-to-one? Right. So if I have an element in the codomain that is nothing mapped to it, again, the function is still not one-to-one because of the behavior surrounding elements 3 and 4 in the domain. But also when I add this d to here, this is also not an onto function. Okay. All right, so now, of course, let's ask a question. What is an onto function? So onto function is also called surjective function. Again, I have function x to y. So f is an onto function if for all element in the codomain y in y, there always exists element in the domain such that fx is equal to y. So that means for all element in the codomain, there's always something in the domain that map to it. So as I mentioned before, this example I just drew, assuming the domain is 1, 2, 3, 4, codomain is A, B, C, D, because the element D has nothing mapped to it, this function is not an onto function. So what is an onto function if I were going to draw a picture of it? If I have, for example, A, B, and C, and I have for every single element in the domain, there's some element in the codomain that map to it. In other way of thinking about it, if I'm thinking about this arrow diagram, there's always an arrow that's point to an element in my codomain. So you don't have a scenario like this. Where this particular element has nothing mapped to it. So this is definitely not an onto function. If I have, it doesn't matter how it looks like on the left, but if you look at the codomain, you have an element, remember for all element in the codomain, there is something that mapped to it. So there has to have an arrow that point to it. But in this case, there's no such arrow. So this function is not onto. This one is onto. Okay, so now let's go back to the problem I want you to prove. I want to prove this function is invertible. To prove something is invertible, it has to be both one-to-one and onto. So basically, the idea is simple. We need to prove it's one-to-one. So the first step is to show it's one-to-one. The second step is to show it's onto. Okay? Do I have a volunteer to show it's one-to-one? Remember, the definition of a one-to-one is you start with a pair who has the same function value and show this pair equal to each other, right? Do I have a volunteer? But by definition, one-to-one, we want to start with g of x equal to g of y. We want to show x equal to y. Okay, so the way to do it is you just use a hypothesis. I'm going to assume there's a pair who has the same function value and show those pair of values equal to each other. Okay, so I'm seeing in the chat, someone is saying that, okay, I'm just substituting the function. Great. So I'm going to change your variable from y1, y2 to xy, but the rest should be the same. So we say let xy is in the domain such that g of x is equal to g of y. We just substitute by the formula g of x is equal to 5x minus 7. That means g of x is equal to 5x minus 7. G of y is equal to 5y minus 7. Now I add 7 onto each other, onto both sides. I have 5x equal to 5y, which means x is equal to y. So I start by assuming g of x is equal to gy, and I showed x equal to y. So I just proved that my function is 1-to-1. Now I want to show it's onto. Do I have a volunteer how to do this? Remember the definition? By definition of onto, that means for all y that is in the codomain, there exists x in the domain such that g of x is equal to y. So I need to find for any real number in the codomain, there is a number in the domain that map to it. So how do I find this number?
So Peter said before to use y is equal to 5x minus 7 and then solve for x.
Yes, perfect. That is the right way to do it, but we can write it slightly differently. I can say that, let y, so to run out of space, let's use here. Let y is in the codomain. So we have y is equal to 5x minus 7. So I solve for x. X is equal to y plus 7 over 5. Okay, but there's one crucial part that is missing. Once I solve for x, so which meaning that g of x is equal to y, because I just solved for it. But there's one thing that's missing. I need to prove x is a real number. Because y is a real number, then x is a real number due to the closure property of real number under multiplication, addition, subtraction, and division. That's it. So what I have here, this is more tightly written solution. To prove it's onto, you're really just solving. I mean, of course, here I'm using a variable z, but you're just solving for a mental picture you want to have is you have the function g that map from domain to codomain. And for any element in the domain, I'm going to find an element in the domain that will map to this element in the codomain. That is proving of onto. So I find this one by actually solving the equation y is equal to 5z minus 7, you solve for z. But the important part to actually complete the entire proof is the closure property of real number. Because z is equal to y plus 7 over 5, because y is a real number, you want to say by closure property, z is a real number. So that is a complete proof. Okay, so when I ask a question about proving something to be invertible, you want to pay attention to say, essentially you want to show the function is 1-to-1 and onto, therefore it's invertible. Okay, for example, the picture I drew right here, in the middle, this is a function that is invertible because it's both 1-to-1 and onto. What does that mean? That means I can flip the arrows of this picture here. Okay. But the problem with the third one, like here, the rightmost picture, this is not an invertible function. Why? Because if I invert the direction, I'm going to take A, B, C, D, put it on the left, and 1, 2, 3, 4, put it on the right. What I have is A goes to 1, B goes to 2, okay? But C somehow goes to both 3 and 4. If I have an element that maps to a different element in the codomain, this is no longer a function. Does that make sense? Okay, all right, let's get back to one more practice question. If there's no more question in the previous one, we have gone through proving a function is invertible, which goes to the definition of onto and 1-to-1. Now I'm going to start asking questions about relations. So if I have R is a relation on the set A, which has 3 elements. Whenever we talk about this, it's a subset of A cross A. So in other words, R is a set of ordered pair, right? It takes an element from set A and another element from set A and form a pair, which is connected by a relation. Here, the relation is X is less than Y, which is represented by the less than symbol. So do I have a volunteer? What are the ordered pair in my relation R? I'll take a pair of elements, right?
Peter said 2, 3.
Yeah.
2, 4.
Mm-hmm.
And 3, 4.
Perfect, right? Because those are the only possible pair relation where taking an element from A, take another element from A, where the first element is less than the second element. That's the relation. Okay. Similarly, I'm going to ask the question, if my relation is what we just described, 2, 3, 2, 4, 3, 4, what is the inverse relation? So this is very similar to the inverse of the function, is I change the direction of the arrow. So what is the inverse of this? Remember, the inverse, again, is a subset of A cross A. I'm reversing the arrow between the relations.
Three, 2, 4, 2, 4, 3.
Exactly. And what is the English description of this? What does this relation mean? Previously is less than, right? X is less than Y. Now I'm going to ask you describing this relation in words. It means?
Greater than.
Exactly. So another mental picture you can form is you have, oh, let me draw it bigger. You have 2, 3, 4, 2, 3, 4. You have relation between 2, 3. You have relation between 2, 4. You have relation between 3, 4. Remember, I'm talking about relation, not function. This is not a function, okay, but it's a relation. And then when I revert the relation, I get I get 3, 2, 4, 2, and 4, 3. So that's a mental picture you can have. All right. Those are easy. Let's look at the next one. I have a relation on the set X, which is non-negative integer. So my R is again an ordered pair that is defined by the relation x squared plus y squared is equal to 25. So what is my set of ordered pairs that describe this relation? So I put a hint here. The hint is going to try to find the non-negative integer solution to this equation because this equation describes the relations. Do I have a volunteer? What are the non-negative integer solution to the equation x squared plus y squared is equal to 25?
So 3, 4, and 5, 0.
Something is missing. Remember, it's an ordered
and
pair.
4, 3. 4, 3.
4, 3. And 0, 5. right? Because you are going to permute the ordering, because when you permute, it's a different ordered pair and it still satisfies the equation. Okay. All right. So if you look at this problem, where the tricky part, you want to find non-negative integer solution and you want to be able to sort of permute them. So that's why the relation R has 4 pairs versus 2 pairs. And sometimes you might miss in the solution 5, 0, because they're non-negative solutions too. Okay, those are simple. Now this one should probably also take you between 15 to 20 seconds. We often use directed graph, or sometimes called an arrow diagram, to represent the relation to a set. So I have a relation R and my set X is 1, 2, 3, 4. So I have a set R that have 4 elements. And we're going to use an arrow diagram to indicate this relation that contains the pair 1, 1, 2, 2, 2, 3, 3, 2, and 4, 2. Do I have a volunteer? How does this arrow diagram look like?
So first, you can draw an arrow from 1 to itself.
Yep. So that's the pair 1, 1. Yep.
And then 2 to itself.
Mm-hmm.
Then an arrow from 2 to 3.
Mm-hmm.
And an arrow from 3 to 2.
Mm-hmm.
And an arrow from 4 to 2.
Precisely. That's it. This is my arrow diagram that indicate the relation R on the set X, right? It's also considered as a directed graph. But the important part here is, remember, I can have an arrow from 2 to 3 and an arrow from 3 to 2, and those corresponding to 2 ordered pairs. Okay. All right. We're going to end today's recitation with a slightly hard problem. It's related to the composition of relations. So we want to prove that the composition of the relations satisfy the associative law. What does that mean? That means we want to show if I have a pair of relation R and S composed together, first is equal to R composed with the result of the second and the third. This is what we want to show. But of course, before we do that, let me give you a quick review. What does a composition mean? A pair belongs to a composed relation if there exists an element in the middle such that A and C is part of the first relation and C of B is part of the second relation. Okay. What is my mental picture here? My mental picture here is there's 3 set of relation. Oh, there's 2 sets, so 2 relation, and I'm composing them. I have a relation from A to C through the relation R. I have a relation between C and B through relation S. Then the composition is saying that through those composition, I have a relation between A and B. So that was the composition mean. Okay. So I will give you 1 minute to try to prove this, but I will give you also a hint. Because I want to show the equality between these 2 compositions, and essentially a relation, even though it's a compositional relation, it's still a relation. It's a set of ordered pair. So I am asking you to prove essentially set equivalences. How do I prove set equivalence? If I want to prove the left-hand side is equal to the right-hand side, what do I need? I need part 1. I need to prove left-hand side is a subset of my right-hand side. 2 is I need to prove my right-hand side is a subset of my left-hand side. So for 1 minute, I want you to try to prove the left-hand side is a subset of the right-hand side. That means you want to show a subset relation. Okay, So I'm going to start a timer and you have 1 minute to do it. Now, while you do that, if there's any question, feel free to raise your hand or unmute yourself. Okay. Do I have a volunteer for this? This is probably the hardest question through this current recitation. It's very much a bunch of, what's that right word? Bookkeeping. And it's based on the definition of composition of relations, which is this one here. You can raise your hand or you can unmute yourself. And your solution doesn't have to be perfect. You just need to get the high level idea. I feel like today's session we're suffering from mid-semester coma. All right, let's do it together. Okay, so if I have a set, I want to show the left-hand side is a subset of the right-hand side. All I need to do is to start with an element on the left-hand side and show its element from the right-hand side. So there's a lot of bookkeeping in this case. I'm pretty much going to apply the definition of relation composition like 3 times. So let's start from the first. Whenever I have an element that is part of the relation, you know it's a pair. So I'm going to start with a pair. So suppose I have a pair and I'm going to use AD. And there's a reason why I call it D, not B, but it's just a variable that is an element from the left-hand side. So now, by definition, it belongs to the composition of a pair of relation, even though the first one is also a composition too, but on the high level, it's the yellow part and the green part. So this means there exists, because it's a part of a composition, that means there exists a middle element C such that A of C is part of the first relation and C of D is a part of a second relation. So that's just using definition of composition. And now because I have AC is part of the composition of R composed with S. Again, by the definition, I'm going to decompose this into 2 parts. The yellow part and then the green part. So what I can say is there exists element B such that A of B is in R and B of C is in S. This is again just applying the definition of relation, composition of relations, right? If this belongs to a composition, that means there's a middle element to connect them. That's really what this means. So I have used the definition of composition twice already. And I'm now just going to recombine those results I have obtained. Because what your goal is to reach the right-hand side. So if you want to do that, you need to first find a pair that is part of S composed with T. And I can do that because I already have a few pieces I need. Because B and C is part of S, right? That's the first part. And C and D is part of T. So I'm getting closer to this. Then what do we have? Then we have B and D is part of S composed with T. I'm again using definition of composition, right? If I have C as a connecting element between B and D, then B and D is part of this composed relation. And finally, I need an R, so I need to compose with something that is part of relation R. Because A and B is in R, and we just showed B and D is in S composed with T. So B is a transitional element. This means A and D is part of R composed with S composed with T. That's the end of proof from the first part. I start with an element on the left-hand side and prove it's an element on the right-hand side. So let me use a little bit highlight. I start with the green box. I end up with the green box. And I used the definition of composition 3 times. Okay, so that is a proof. This is a typing proof of what I just went through. And I would encourage you to try to prove the second part in your spare time. It's the same kind of concept, but it's useful for you to keep track of this relation, right? Again, you start with an element AD that is a part of this composition, and you want to show it's part of the right-hand side. So this would be a take-home practice for you. Then the hope is by the end of this problem, you will be very familiar with the definition of what is a pair composition. What is a composition of a relation, okay? I can make this life a little bit more complicated by doing 3-way composition. This is a composition of 3 relations. I can do a composition of 4 relations, but you could imagine the proof is the same. In fact, I could even create a problem that I'm going to ask you for induction proofs of compositions. You can prove composition with 3 elements on top of with 4 elements as an induction on the previous case with a composition of 3 elements. Anyway, so as you can see, as we move on to the next chapters, the type of problem you're going to see is going to be a combination of new concept and proofs. So that's why I was saying that quiz number 2 is usually the hardest, because you are still getting used to how to do proofs. But the proof is going to show up again and again with respect to new concept. And later on, we are going to learn combinatorics, which is probability and counting. So in there, algebra is going to play a major role. So yeah, it's going to be lots of fun. Okay, any questions?
Someone's asking in the chat if the 3-way composition type of problem would be in a test.
No promises. If you understand the definition, it should not be. If you know how to prove this type of question, a similar question should not be hard as long as you understand what the definition of a composition is. But I'm actually not the one in charge of making the next quiz, so who knows what the other professor might ask. But it's going to be on the question of, next quiz number 3 is on sets. And quiz number 4, I believe, is going to be on relation functions. So yeah, no promises. Okay, if there's no more question, have a good week. Stay safe and healthy, and I will see you next Tuesday.